Okay, so today what we're going to do is continue on with the discussion about rotation, rotational motion, and then absolute motion we'll get into, which what we're going to end up seeing here is we're going to come up with a geometric type of description to what we see in a mechanism, and then using that geometric description, we will then take derivatives to find out the velocity and acceleration information we need. So first of all, I'd like to just point out in the text a summary of what I gave you the other day, last session. And here on this page, these are fundamental relationships. These are analogous to what we started the course with.
What page?
Page 334, 334. It's analogous to velocity. This is angular velocity, being the time rate of change of angular displacement. Angular acceleration, being the time rate of change of angular velocity. Eliminating the time dependence in those differential equations, we come up with omega d omega equals alpha d theta. You just have to be careful to use them in a similar fashion to what you experienced early in the course in the rectilinear motion. Over on the next, here down at the bottom of this page, you'll notice the following. So what do you need to make sure you're cautious of? I'm going to put my hand above this. So what do you need to make sure you're cautious of if you're going to use these equations you see down here?
Thompson angular acceleration.
Okay. Was that out of your brain or out of the book?
Well, I kind of figured that's what it was because they look like the other projectile motion.
Very nice. And you notice in the sentence I covered that up right above these equations. That's why I was checking with you. As it says, for rotation with constant angular acceleration, you could then use these simplified formulas. Don't use them incorrectly if the angular acceleration is variable. Okay. Then rotation about a fixed axis. Let me just show you this. Here's what we discussed yesterday. V is r omega. The normal acceleration is r omega squared. Occasionally, you might actually want to treat it as v times omega. So it's r omega omega, which becomes v omega. And then the tangential acceleration component is r alpha. Then near the end of class yesterday, we ended up developing what you see down here in these two figures, where we can see the normal acceleration directed back towards the axis of rotation, and it's omega cross r. And then the tangential acceleration is perpendicular to the radial arm coming out, and it's alpha cross r. And then the velocity is omega cross r. Then finally, on the top of the next page, they went through this development, which we discussed yesterday, last class session, where we end up coming up with these cross-product relationships for the vector quantities. Notice the bold-face type for the vector quantities, the acceleration components, and the velocity. Okay, so that was a quick summary of what we covered last class session. And then there are some introductory problems. So what I thought we might do is take one like this, just to get our feet on the ground here. Number 12 here. We have a right angle bar with a pin P that's up 50 millimeters up off that plane, and it rotates about the z-axis through O. Here's point O, z-axis through O, and it has an angular acceleration opposing, notice there are arrows up here, the angular acceleration is opposing the angular velocity. So what physically is happening to the mechanism? It's slowing down, okay? Slowing down. Determine the velocity and acceleration of point P out here when the angular velocity reaches the value of 2 radians per second. So, I was just wondering if it starts from rest or not. It doesn't indicate that. Okay, so let's go ahead and put that information up on the board. And in brief summary, V equals omega across R. The normal acceleration is omega cross R. Tangential acceleration is alpha cross R. So this particular problem has a mechanism that looks like this. That's a right angle. That's a right angle. Here's point P. Here's the axis of rotation. Given the omega of 2 radians per second, we have the alpha going the other direction, and its magnitude is 3 radians per second squared. And we have some dimensions of 1/2 meter, 2/10 meter, and 5/100 meter up to point P. And the question's asking for the velocity and the acceleration of point P. So I think everything is there. Oh, they also define some axes for us. So our x-axis is projected this direction. The y-axis is that way, right-hand rule, and then z is upward. So what we need to be able to carry this solution out is we need to form the position vector. We need to form the vector for the omega and alpha. And those are the components that make up the velocity and acceleration components then for us. So this takes you back to your statics. From the axis here, we're going to go 0.5 I plus 0.2 J plus 0.05 K. Omega is in the positive Z direction, so it's 2K, and alpha is negative 3K. So to find the velocity, it's omega cross R. So this is a very elementary problem, but I wanted to go through this with you just to make sure your vector algebra skills are in place. Omega cross R, 0.5 I, 0.2 J, 0.05 K. Notice Notice that the physical mechanism here, this point P is physically up off the plane of the angle rod here. It's physically up. So that K reading of 0.05 should have nothing to do with the angular speed around this axis over here. And you can see in the cross product that this K cross K term zeroes out. All right? Everybody comfortable? K cross K zeroes out? Okay, so all we're going to have is K cross I and then K cross J showing up. Now, there's a quick way to do those cross products in your head. What technique do you folks use? If you're doing K cross I or K cross J, how do you folks determine? Do you take your right hand and play the game with it, or what?
I usually just go out a matrix on some scratch paper.
Treat it as a matrix and then work it out that way?
Mm-hmm.
Okay? You don't need to, many times. So it's going to be a little quicker for you if you think of I, J, K, and if you go alphabetical in that direction, your cross product of any pair there in that direction are going to be the other one. If you go the opposite direction, it's going to be negative. So K cross I is in the correct direction, so you're going to end up with a J component coming out of that cross product right here. K cross J is going to be negative I. That's handy. It's going to save you time. The more complex problems, you'd set it up as a matrix and handle the cross product that way. Okay? So we're trying to help you be efficient and at the same time know more than one way to handle these things. So if I want to form my I term first, I'm going to go K cross J is negative I, so I'm going to end up with a negative 0.4 I. K cross I is J, so that's going to be my J term, K cross I, and that's going to be half of 2 is 1, so plus 1J, and the units on that are meters per second. So that answers the velocity question. Okay? To obtain the acceleration is made up of the normal and tangential vector components. So the normal term is going to be the omega cross r plus the alpha cross r. Now here's where you can use the previous work that's been done, because omega cross r is, as I noted at the beginning of class out of the textbook, that's V. So since we did that work right here, it's going to just make the work, instead of dealing with a triple cross product, it's going to be easier for us just to treat it this way. So the acceleration at point P then, and this is point P, is going to be our omega, which was 2K, crossed with our negative 0.4 I plus a J term. And then we add to that a negative 3K crossed with our original R. 0.5 I plus 0.2 J plus 0.05, sorry about that, K. Put parentheses around that. I'll just come over here. So the acceleration of P is then going to be equal to K cross J is going backwards, right? K cross J is backwards alphabetically, so you're going to end up with negative I, and you're going to end up with a negative 2I. And this term right here, K cross I, is in the negative negative becomes, you with me? Negative negative becomes positive. So we end up with 8/10, positive 8/10 J.
Okay, so I thought you said when it's K cross I, then it's positive J.
Oh, I did. I was thinking alphabet. Let's see, K cross I. Oh, that is in the correct rotation, isn't it? Yeah. Okay, thank you. We don't want any sign errors. Okay. So where was I? K cross I is J, right? So that's negative then. J. Is that correct? Now, how can we check that without doing some other math? It better be pointing effectively back towards the pole, right? Towards the axis of rotation. So it better be pointing back this way. Right? Back towards the axis of rotation. See, that point P is in circular motion, remember. It's in circular motion around this axis of rotation. So that normal component better be pointing back. So it's not just cranking out the math. You want to think about these terms. And you can look at this ratioing right here. This ratio is a 2 to 5 right here, isn't it, in the geometry? The 2 to 5. So this thing better exhibit a 2 to 5 ratio regarding its y component and x component. And you can see 5 times this is, whoops.
Double the small one and
No, that's right.
Is this right?
Because if you multiply the 0.2 by 4, you get 0.8. Multiply 0.5 by 4, and you get 2.
Okay, thank you. Good, the arithmetic got me. Okay, so do you see how you can double check yourself? And it's always worth taking a moment to double check yourself on something like that. Okay. Could you do something before we continue on with that acceleration? Could you, because we haven't finished it yet, could we do something back here on the velocity to see if that was right? That should be pointing perpendicular to this arm right here, shouldn't it, in the plane of the rotation? Okay, so it should be pointing with a negative x term and a positive y term. A negative x term and a positive y term. And it should be in the reciprocal of the 2 to 5 ratio. 5 to 2. And that should be exhibited in those numbers as well. Okay? 5 to 2 is 2.5 to 1. And you can see those 2.5 of this is 1. Okay. Always try to pause when you see something like that and see if you can look at it in a visual perspective to make sure you're on the right track. Comment?
First question. When it's not specified in this case, it's safe to assume to use vectors, right? Give the answer in vectors.
Yes. Matter of fact, you may not need, in whatever your major is, you may not need another dynamics course. But I can guarantee you in upper division engineering work, vectors are going to be your friend. So that's why the rest of this course is going to be pretty much vector algebra and calculus type stuff. So it should help strengthen your skills in those areas. Okay.
The magnitude velocity should be omega r, right?
Yes. And let's get to that. We'll double check it. We'll check that as well in a few minutes. And the same on your normal acceleration, your r omega squared, should be showing up as well in this in these items as well. So let's finish off this acceleration. So we did the first cross product. Now we have to handle this cross product. So let me get the I term first. That's going to come from K cross J. K cross J is negative I. So negative times a negative is going to be a positive 0.6 I. And then we're going to do k cross I is in the correct order of the rotation, k cross I. That's going to be our j term. It's going to be half of 3, so minus 1.5. And this term is our tangential term, isn't it? The alpha cross r we just did. Okay, and this one should point in the same direction as what?
The velocity.
You all with me on this? These last two should point, as Daniel said, in the direction of the velocity. And so what you can do is you can look back at your velocity and see that you're a 2.5 to 1 ratio there, and we should see a 2.5 to 1 here also. And let's see, is that right? Oh, I'm sorry. What's noted? See the minus plus? What's going on there?
It's opposite direction of velocity.
Yeah, it's backwards because it's slowing down, as we said when we first started the problem, okay? But the geometric ratio of this should be consistent with your velocity components. Okay. Feeling good? Then we just tidy that up a little bit, and we end up with minus 1.4 I and a minus 2.3 J acceleration. If we looked down, this is an elevation view, sort of, or a perspective view. If we look down from the top on a plan view of this, then what we would see is this circular motion on this lever arm, which would be on a lever arm of 0.1 square root of 29 is the length of that bar. If I took the L out of it and just went straight across to this point, down just below point P, this would be our lever arm. I'm just looking at the scaling 2 to 5 here. Getting the square root of 29 factor with a 10th tossed in as a multiplier. So if we look down on the top of that, then this lever arm would be 0.1 square root of 29, and our velocity should be pointing perpendicular to that with the r omega reading for the speed. And there should be a normal acceleration pointing back this way, which is an r omega squared reading. And there should be a decelerating component, r alpha. And it would be worthwhile to check to see what those scalar values are. So do we use all of, now here's where you got to be a little careful. Do you use that 0.05K in your R? No, you do not. Because think about what that would be. That would be tilted up off this. And so we have to make sure that we carry these cross products out carefully. So it's not just the, to do this, I should tag this R. Maybe I should call this an effective R in the plane of the rotation kind of a thing. So let me call that a capital R so you don't confuse this R with the magnitude of this 3-component vector. So the R the capital R, is the square root of just the 0.5 squared plus the 0.2 squared. Okay. Let's not take the time to finish that off.
Then you
Yeah.
multiply that by omega, you do get two different.
Well, actually, that's 0.1 square root of 29, isn't it?
Yeah.
Yeah.
Yeah. So that's going to be 0.1 square root of 29. So this is our effective R. And then actually we can go ahead and do that since we have the 2 and the 3 on those readings. So this guy up here then is going to be equal to 0.1 square root of 29 times R omega, which was a 2. And then our R alpha is going to be the 0.1 square root of 29. Let me turn this around so you can see a little better here. There we go. Try to get the reflection off of that, times the alpha, which is the negative 3. And actually, I'm not even going to, I'm going to take that 3 off of there, the negative off of that, because I have the arrow here indicating its direction. And then the R omega squared, you could kick that in there as well. 0.1 square root of 29 times your omega squared would be a 4 multiplier on that. And that should, those values should come along with, like the magnitude of this first part right here is your AN vector, and its magnitude should go along with the calculated value we saw over there. And so that would be a 4 plus 0.64 square rooted, leg squared, which should be a touch over 2. And that should be the normal term. Do those values check out?
They do.
Good, thank you. Okay. So there should be consistency between the direction information from the geometry here and then the vector calculations and then the magnitudes of these vectors as well. Okay? Let's do one like this, right down here at the bottom of the page. A variable torque is applied to a rotating wheel at time 0, causing a clockwise angular acceleration to increase linearly with a clockwise angular displacement theta of the wheel during the next 30 revolutions. When the wheel is turned an additional 30 revolutions, its angular velocity is 90 radians per second. Determine its angular velocity at the start of the interval at time 0. Now they gave us a graph that's shown at the top of the next column, and I'll put that up on the board. Okay, everybody got the idea of the question?